So we have an aircraft. Here we go. We have an aircraft, small engine, single engine plane, one of those like Cessna, is flying in this direction. It is going at a speed of 110 miles per hour and is heading in this direction. Direction, I don't know, let's say this is 37 degree. Now we got wind blowing. And the wind blowing, this is the north, south, east, and west. Let's say we get the wind blowing in this direction, blowing north. And it's a good speed wind. It's gusting at 40 miles per hour. What's going to happen to that airplane? If I'm the pilot and I'm flying that plane, I point, let's say my runway is right here. There's the runway. I'm heading toward that runway. Because the wind is going 40 miles per hour in that direction, if I don't pay attention to that wind, I'm going to end up going in that direction and landing somewhere else. So, right there. I'm going to end up heading that direction. So the question is, if I don't pay attention to the wind, if I neglect the wind as a pilot, which way I'm going to be heading and how fast I'm going to be going? So if I neglect the wind, I don't want to neglect it, but if I was stupid enough not to pay attention to it, if I neglect the wind, what direction will I fly to, and what is my speed? So I'm going to have the two vectors, add them, and see what the result is. I'm going to do the same thing, vector addition. I have two vectors, if you remember. So the first column is going to have the vectors in it. Then the next column is the x component, then the y component. X component, and x equals r cosine theta, and the y component, r sine theta. So my first vector is the airplane. Vector A is the airplane. The airplane has a speed of 110. In which direction I have the plane pointing? As a pilot, I just put a 37 degree, and I set the GPS to 37 degrees is going that direction. Or what is that? Autopilot. I set the autopilot to 37 degrees is going that direction. So my x component is going to be 110 cosine 37, and my y component is going to be 110 sine of 37 degrees. So here's my calculator. Let's see. My cheap calculator again. Turn it on. Clear that. 110 cosine 37 degrees equals 87.85. And the y component is going to be 110 sine 37. And that's 66.20. The wind is at 40 miles per hour in what direction? 90 degrees. So 40 cosine 90 degrees, which is 0, and 40 sine the 90 degrees, which is 40. So the result in the x direction now is going to be 87.85. The result in the y direction is going to be what? 106.20. What's my speed? That's the result. How fast I'm going. It is the square root of the x value squared plus the y value squared. 87.85 squared plus 106.20 squared. And let's see what that number is. The square root of 87.85 squared. Where's the square? Plus 106.20 squared. And I got 137.8 miles per hour. Notice I'm going much faster than the plane is telling me. The plane is saying you're going, the instrument's saying I'm going 110 miles per hour. But I'm really going 100 and almost 40 miles per hour, 137.8. Because I got what? I get tail wind. I get the wind pushing me from behind. And my angle is I'm going to be drifted. It's not going to be 37 degrees. It's going to be more than that. So theta is going to be the inverse tangent of the y value over the x value. The y, which is what? 106.20. The x value 87.85. Second tangent, parentheses, here we go, 106.20 divided by 87.85. It's 50.4 degrees. I missed it by 13 degrees. Now 13 degrees doesn't sound a lot, but if you go in long distance from Boston to California, that 13 degree could end up being about 150 miles away from where you're heading. If you're going from Boston to New York, that's not that far. That distance might be like 20 miles, 15 miles. So instead of landing in JFK, you land LaGuardia. That's one application for forces there. Let's get one not too technical. A lot of physics problems here, but we'll get one. I'll think of one. Here is another one. I got an idea. I love watching this show, Mega Boats. They show you these cruise ships or big boats, massive. And And once they finish with them, now they got to move them. And to move them, especially in a small area, it is tough. So they bring in the tugboats, and the tugboats have to pull them out of that little, channel there to get them where they're going. So we have a cruise line here, big ship. I don't know, this is my ship here. This is the ship, I don't know, this is like layers on it, I don't know. And now you gotta move that ship. And to make sure the ship is safe, they're bringing 3-4 tugboats. And we got one tugboat is pulling in this direction of a force, let's say 5,400 Newton. That's a force. I might have another tugboat pulling in that direction at an angle, let's say of 50 degrees here, of a force of 3,200 Newton. Then I got a tugboat pulling in this direction. We'll say this angle is 20 degrees. And the value of that 4,000 Newton. And let's add one more, pulling backward to make sure it doesn't slam, doesn't go forward. You want to stop it there. We got another tugboat pulling back here, straight back, of 2,000 Newton. And my goal is to take these 4 tugboats that I have there and find the net result of them. Like if I was to get one tugboat to do the work all 4 did, what is the value of that, how strong that tugboat, and what direction should I make it go? So here's my forces. When I put them in, let me draw a picture of it. I have one in this direction. That's 5,400 Newton. I got one pulling back, and that's 200 Newton. That's this one. I got one pulling a direction of 50-degree angle in that direction. This is 50 degrees here of 3,200. And I got one pulling down in this direction, another one of 4,000. And the value of the angle is 20 degrees. These are all the forces I have working on that cruise line. What's the net force? Can we find what that net force is? I'm going to take these 4 vectors, add them, and see what the net result is. And when I go to add them, I'm going to make my own table. So this is a mega ship. Mega ship problem. And we have 4 tugboats pulling on it. So I'm going to add these 4 forces here. So I'm going to make my table here. There's my table. There's the label on the top. This is the first force. The second force. I got 4 of them. The third force. And the fourth force. An X and Y component. There we go. So vector here, X component, and x equals r times cosine theta. I'm reminding you of that. Y component and y equals r sine theta. Let me label these vectors, vector A, B, C, and D. Let me label them, A, B, C, D. Let's look at vector A. What's the value, what's the direction? 5400, in what direction? 0 degree. That's vector A. Vector B. B is this one. What's the value? 3200. In what direction? 50. Vector C is what? 200. In what direction? What's the direction for C? 180. You're going backward. You always measure from this line, from the positive. And vector D, and the value of D here is what? 4,000. In what direction? I can use negative 20, or I can use what? 340? Doesn't matter. So you can use a negative value. So let's find the x and y component. We'll call that A of x in the x direction, which is 5400 cosine of 0. AX equals 5400. A in the y direction, 5400 sine of 0. A in the y direction, that's a 0. Let's find the x component vector B. 3200 cosine 50. There we go, 3200 cosine 50. And it's 2000. 2056.9. I'll just go one decimal place. And the component in the y direction is going to be 3200 sine of 50. And it's by equals what? 2451.3. Tugboat C, the one pulling backward, x component is going to be 200 cosine 180. Negative 200. In the y direction is going to be 200 sine 180. 0. And the last one, that one on the bottom, D there, in the x direction is 400 cosine negative 20. .400 cosine I got 375.9, and the y value, oh, that was 4,000, was it 4,000? 400. 4,000. Okay. 3758.7 or 0.8. And in the y direction, that was a 4,000 sine negative 20 degrees. And that's a negative 1368.1. So I get the x and y component for each tugboat, every one of them. Now you take them and add them, and that's the result in x. And you add them, and that's the result in y. Let's see what the result in x. 5,400 plus 2056.9 minus, is that 2,000 or 200? Or we're in the 1,000. Minus 2,000 plus 3758.8. The result in the x direction, 9,215.7. The result in the y direction, 2451.3 minus 1368.1 the result in the y direction, 1083.2. You plug in these numbers into that. The square root of parentheses 9215.7 squared plus 1083.2 squared I need a big tugboat with the force of 9,279.1 Newton. That's how strong we'll have to be. In what direction is it going to go? Notice R sub x is positive, no adjustment of R sub y to R sub x. And R sub y is 1083.2, R sub x 9215.7. One 1083.2 divided by 9215.7, and it's 6.7 degrees. So you get a huge tugboat. It can be just a little bit off, instead of horizontal, just a hair off, 6 degrees, 7 degrees almost, and start pulling, and that'll give me the same result. That's the direction actually that cruise line or the mega ship is going to travel. It's going to travel in that direction. So if we get a tugboat that's strong enough to pull that with the force of 9,279 in this direction, that'll be equivalent to the 4 tugboats we have working together. I mean, there's lots of places there we can use vectors. I'm just thinking of some of the applications. Okay. I'll throw another application there. You're picking an engine from a car. I don't know what the engine looks like. Block, the door block of engine, I don't know. Well, just like a concrete, we'll use a concrete, it doesn't have to be an engine. You're trying to raise a concrete block there. Usually you attach a rope to it. You put it over a pulley there, that rope. And it comes down here in this direction. And here we have two people pulling, and there's like another pulley here, if you want it. We have a ring with it attached, two ropes. One person's pulling in that direction of 490 pounds. And one person's pulling in this direction of 220 pounds. And let's say we're holding that engine from moving. I'm holding it. The question, what is the weight of that engine? How heavy that engine? The weight of the block. How heavy is it? Well, the fact the block is not moving, I'm holding it there. It's not moving. The fact the block is not moving, this block has a weight that's pulling down. And the reason it's not falling, why? Why isn't it going to the ground? Because you got this cable pulling up back on it of the same force. Of the weight, right there. The force have to be equal. If they weren't equal, one of them will move. If this force was stronger than that, the cable will snap, will fall down. If this tension in the cable was stronger than the weight, it will move up. The fact things is not moving, we call that in physics, what is it? Stationary. And stationary means what? We have something, we call their name. Anyone took physics? Nobody? Okay. No big deal. You don't have to know the name, but the fact is not moving. That means the net force equals zero. Actually, the name, if you want the name, is called equilibrium or balanced system. You have an equilibrium system. The net forces is zero. That means the weight has to equal to the tension in the cable. They have to be. So the tension here has to equal to the weight if it's not moving. Well, this tension is the same tension as that, the same cable. So the weight equals the tension in the cable. Well, if I know what that value is, I know what the weight is. The weight equals the tension. Well, the fact it's not moving, that tension has to have a force in this direction, because if it's not moving, you want a force in that direction to equal what? 220 pounds. They have to be equal to each other to cancel each other out. It has to have a value in this direction of 490 pounds. That's what that tension should have. It should have a component in this direction equal to that, and a component in this direction equals to this. If they are equal, they cancel each other out. That means equilibrium, the net force is zero. There is no net force in this direction, they cancel each other out. There is no net force in that direction, they cancel each other out. So now I know the tension, it has a component in the x direction of negative, because going to the left, 490 pounds in the x direction. That little hat over x, it means in the x direction. And it has a value in the y direction of how big in the y direction? Positive 220 pounds in the y direction. That's what the tension is. Now I need to find out what the x and, this is the x and y component. I want to change them now to r and theta. You know the x and y component. How do you find r, or the value of t? It is the square root of the x component squared plus the y component squared. And let's find out what that number is. The square root, parentheses, of 490 squared plus 220 squared. It's 537.1 pound. That's the tension in the cable. That's the value of it. And the angle theta, it's the inverse tangent of the y value over the x value. Y here is what? 220, x is negative 490, and since x is negative, you need to add 180 degrees to the answer. I don't know how to make the angle negative here on this calculator. Let me see if I can find it. I have no idea how to make plus minus on this one. I don't see it. So I'll just divide them without, I know which quadrant is going to be. Did we get what? What value? 153.4. So when you measure that angle, that tension in that cable that's holding that engine, if you look at that tension here, we're looking at it, it's going like this. This is 153.4. And the value of that is 537. And it's holding that engine here. So that's how much that you need a cable to handle, a little bit more than that value, because in case we push down on it. So usually for safety reason, you might get a cable that will hold about 800 pounds. If you buy one that will hold 530, 540, you're looking for trouble there. Because once I put my hand on it, I'm pushing down, that cable will snap. And if somebody's under the car and trying to guide it, we just lost that person. So you get something probably twice that, 1,000 pounds. Just so you know, I know it's 537, but let me be on the safe side. Maybe I'll use 2 cable just in case one snaps, I have the other one holding it. But that's an application also for vectors, where we use vectors.